Hi everyone, my name is Pavitra V, Department of Chemistry. Today we are going to discuss a topic called chemical kinetics, which is comes under 4th semester SEP syllabus, complete chemical kinetics. So chemical kinetics is a branch of physical chemistry which deals with the study of rate of chemical reactions with respect to time. So first we will discuss the definition of rate of reaction. Rate of reaction is nothing but R is proportional to dx by dt, change in concentration with respect to time. So when we consider the reactants and product concentration during the reaction, the concentration of reactants decreases with the time and the concentration of products increases with time. You can see in the graph. So decrease in the concentration of reactants is denoted by negative sign minus dx by dt, and the increase in concentration of products is denoted by plus dx by dt. So this is the graphical representation. Next we will discuss order of reaction. Order of reaction is nothing but sum of powers of molar concentration terms of all the reactants in an experimentally determined rate equation. So consider a reaction of type alpha of A plus beta of B gives rise to product. When rate equation is written as rate is proportional to molar concentration of A to the power alpha and molar concentration of B to the power beta. The order of reaction is sum of the powers of molar concentration terms, that is alpha plus beta. Alpha plus beta may be equal to 0, 1, 2, 3, etc. If it is equal to 0, then it is called zero order reaction. If it is equal to 1, then it is called first order reaction. If it is 2, then it is second order reaction, and so on. Next is unit of rate constant. So when we discuss the unit of rate constant, we can easily remember it by a general formula: mole to the power 1 minus n, liter to the power n minus 1, and per second. So for zero order reaction, n is equal to 0. Substitute n is equal to 0 in the above general formula. We will get a unit rate constant unit as mole per liter per second. For first order reaction, n is equal to 1. The unit is per second. For second order reaction, n is equal to 2. The unit is per mole liter per second, and so on. So second order reaction, the differential equation, consider a reaction 2A gives rise to product. So rate is proportional to molar concentration of A to the power 2 because it is a second order reaction. The differential equation is given as K is equal to 1 by T into 1 by A minus X minus of 1 by A. So here A is the initial concentration of reactant at a time T is equal to 0, that is before starting a reaction, and X is the amount of reactant reacted at a time T, and A minus X is the remaining concentration of reactant after time T. So we have a derivation of second order rate equation when A is equal to B, that is initial concentration, same initial concentration of two reactants. Hence, we are considering a reaction type 2A gives rise to product. The rate equation is written as dx by dt is proportional to molar concentration of A to the power 2. So here we are considering small letter a is the initial concentration of reactant A, and the amount of reacted is x mole per dm cube at time t. Then we have a molar concentration of A will be equal to A minus x. Dx by dt is proportional to A minus x to the power 2. So here we are removing proportionality symbol by introducing a constant and equals. So rearranging the above equation, x terms to the one side and dt terms to the other side. So we are integrating the equation. We are getting integration of dx by a minus x whole square is equal to k into integration of dt. So the integration of 1 by x square will be equal to 1 by x. So here 1 by a minus x is equal to kt plus c. C is the integration constant. So in order to derive the expression for integration constant, consider the reaction t is equal to 0. At the time t is equal to 0 before starting a reaction, x is also equal to 0. Then substituting in equation 1, we will get c is equal to 1 by a. Substitute equation 2 in 1, we get 1 by a minus x is equal to kt plus 1 by a. That is, after simplification for k, that is rate constant, k is equal to 1 by t into x divided by a into a minus x. So the half-life period of second order reaction, which is continuation for a is equal to b derivation. So we have half-life period is nothing but the time required to reduce the reactant concentration to exactly half of its original concentration. That is, x is equal to a by 2. A is the initial concentration divided by 2. The time required is t is equal to t half-life period. So we have a equation k is equal to 1 by t half into, for x we are substituting a minus x in the above equation. So after simplification we will get t half is equal to 1 divided by a into k. That is, we are replacing equals and a constant by proportionality symbol. Half-life period is inversely proportional to the initial concentration of reaction. Next derivation is expression for rate constant of second order reaction when A is not equal to B, that is, two reactants having different concentrations. Hence we are considering a reaction of type A plus B gives rise to products. So we are considering the initial concentration of capital A reactant as a small letter a mole per dm cube, and initial concentration of reactant B as small letter b moles per dm cube. After time t, x moles of A moles per dm cube of A and B are reacted at the same time. Hence, the remaining concentration of A is A minus x and B is B minus x moles per dm cube. So, we are applying law of mass action. Dx by dt is proportional to molar concentration of A into molar concentration of B. So, we are substituting the molar concentration of A as A minus x and B as B minus x. So in order to remove the proportionality symbol, we are introducing a constant k and a equal symbol. Rearranging the equation, x terms to one side and dt terms to other side. So for the simplification, before integrating, we are applying partial functions. That is, 1 divided by a minus x into b minus x will be equal to 1 divided by a minus b into 1 divided by b minus x minus of 1 divided by a minus x. So after integration, integration of 1 by x will be equal to log a minus x, and we have a minus x. The successive integration will leads to minus 1, multiplication of minus 1. Hence we get 1 by a minus b into minus of log b minus x minus minus of minus log a minus x. So we are applying logarithm equations, that is, log a minus log b is equal to log a by b. So we are getting then integrating constant c, and we are calling this equation number 1. In order to get the integration constant equation, once again we are considering when t is equal to 0, then x is equal to 0. So 1 by a minus x log of a minus a divided by b is equal to c. Substitute equation 2 in above equation 1, and after simplification we are getting the final equation k is equal to 2.303 divided by t into a minus b log to the base 10 into b into a minus x divided by a into b minus x. Next, we will move on to examples of second order reaction. First one is the saponification of an ester, that is, ethyl acetate ester is treated with a base NaOH to give acid salt, sodium acetate, and an ethanol, which is an alcohol. Next is decomposition of hydrogen iodide. 2 moles of HI will give you hydrogen and iodine. Thermal decomposition of acetaldehyde, CH3CHO, gives you 2 moles of CH4 methane plus 2 moles of carbon monoxide. Next, decomposition of NO2. 2 NO2 gives rise to 2 NO plus O2, oxygen. Gaseous decomposition of HCl. 2 HCl gives rise to hydrogen plus chlorine gas. Next is formation of ethyl acetate. CH3COOH, acetic acid plus ethanol gives you ethyl acetate plus water. Next is experimental verification of second order reaction, study of kinetics of saponification of an ester. So in this reaction, ethyl acetate is treated with sodium hydroxide to form sodium acetate and ethanol, that is ethyl alcohol. So here we are considering the decrease in the concentration of NaOH as the reaction proceeds. So the concentration of NaOH is determined by titrating the remaining reaction mixture NaOH by titrating it against an acid, standard acid. So we can write as volume of the standard acid used at the beginning of the experiment at time t is equal to 0. We will get V naught as the volume, and that will be proportional to initial concentration of NaOH. That is next after time, every time intervals we are taking the reaction mixture and we are titrating it against a standard acid. So in that case we will get volume of standard acid solution used at any instant of time, that is t. We will get the volume Vt, that will be proportional to concentration of NaOH at that instant, that is A minus X, remaining concentration of NaOH. So the overall conclusion, that is A is proportional to V naught and A minus X is proportional to Vt. And for equation 1 we are substituting A minus X is proportional to Vt, then A minus Vt is proportional to X, that is V naught minus Vt is proportional to X. We are substituting equation 1, 2 and 3 in the rate constant equation, that is K is equal to 1 by T X divided by A into A minus X. Substituting the X value, A value and A minus X value, we are getting K is equal to 1 by T V naught minus Vt divided by V naught Vt. Next we will move on to determination of order of a reaction. We have three methods for the determination of order of a reaction. In that, the first one is differential method. In differential method we are considering Van 't Hoff's differential method. So we have a nth order proportional to nth power of concentration rate equation, that is minus dC by dt is equal to K into C power n. Considering this rate equation at two different concentrations C1 and C2, we are getting minus dC1 divided by dt is equal to K into C1 to the power n, calling this equation number 1, and similarly minus dC2 divided by dt is equal to K into C2 to the power n, equation 2. So we are taking log function for equation 1 and 2, we will get this equation 3 and 4. When we consider logarithm functions, log a into b is equal to log a plus log b, and another equation log a to the power n is equal to n log a. So we are applying logarithm equations and we are simplifying, we are getting equation 3 and 4. Now next step is subtract equation 3 by equation 4, and after simplification we are taking the n terms one side and other concentration terms other side. We are rearranging the equation to get final equation as n is equal to log of minus dC1 divided by dt minus log of minus dC2 divided by dt divided by log C1 minus log C2. So this is the final equation where n is the order of the reaction. Here we are plotting a graph, concentration against time t. We are getting a slope minus dC1 by dt and minus dC2 by dt, and from the substituting these values in equation 5, we can calculate n. Next method is half-life method. We are considering the half-life of a reaction at two different initial concentration A1 and A2. We know that half-life T half is proportional to 1 divided by molar concentration of A to the power n minus 1. A is the initial concentration. We know that half-life period is inversely proportional to the initial concentration. So n is the order of reaction. We are considering at two different initial concentration, hence we will get two different half-lives T1 and T2. T1 is proportional to 1 divided by molar concentration of A1 to the power n minus 1, and T2 is proportional to 1 divided by molar concentration of A2 to the power n minus 1. So we are dividing equation 1 by 2 T1 divided by T2 is equal to, it will become reciprocal denominator, because it is 1 by A2. Hence we will get A2 divided by A1 whole to the power n minus 1. We are taking log on both the sides. We know that logarithm function log a to the power n will be equal to n log a. Hence we are simplifying it and we are taking n terms one side, and final equation will be equal to n is equal to 1 plus log t1 minus log t2 divided by log a2 minus log a1. So this is the half-life method to calculate the order of a reaction. Next, the third one is isolation method. In isolation method, consider a reaction N1 of A plus N2 of B plus N3 of C gives rise to product. Here A, B, C are the reactants. The rate equation is given by dx by dt is equal to K into molar concentration of A to the power N1 and molar concentration of B to the power N2 and molar concentration of C to the power N3. The order of reaction will be given as N1 plus N2 plus N3. So this is the overall order of a reaction. In order to calculate this, we are taking three cases. In case 1, we will take small amount of reactant A in order to calculate N1 and excess of reactant B and C. So when it is excess, the change in concentration can be neglected, so that we can only concentrate it on reactant A to calculate N1. Similarly, in case 2, to calculate the N2, we are taking A and C reactants in excess, so that the change in the concentration can be neglected. We can concentrate only on the change in concentration of reactant B, so that we can calculate N2. Similarly, to calculate N3, we are taking A and B in excess, and we can calculate N3. Substituting the overall results, N order of a reaction, overall order will be equal to N1 plus N2 plus N3. This method is called isolation method. Next, we will discuss the effect of temperature on rate of reaction. So it is found that increase in temperature will definitely increase the rate of reaction. That is, up to rise in temperature up to 10 degree Celsius will increase the reaction rate by 2 or 3 times for every 10 degree rise in temperature. That is given in a ratio form. The temperature ratio K of T plus 10 divided by KT. This ratio is called temperature coefficient. That will be equal to K into T plus 10 divided by KT is equal to 2 or 3 times, which increases the rate of reaction. Next, we will discuss the Arrhenius equation. So we have a Arrhenius equation K is equal to A into e power minus EA by RT, where A is the Arrhenius factor, EA is the energy of activation, that is activation energy, R is gas constant, and T is absolute temperature. For the above equation, we are taking log on both the sides. Log K will be equal to log AB will give you log A plus log B, but log to e to the base any to the power anything will give you that quantity. Hence log A minus EA by 2.303 RT, because we are taking 10 to the base. So here we are plotting a graph log K versus 1 by T. So we are getting a slope. That slope will give us minus EA divided by 2.303 R. By using the slope calculation, we can calculate the energy of activation. This is the graphical method of Arrhenius equation. For the derivation purpose, we are considering the reaction at two different temperatures T1 and T2. When we consider two different temperatures, we are getting two different rate constants K1 and K2. The equation is log K1 is equal to log A is constant, minus EA by 2.303 RT1. Energy of activation for a reaction is also a constant. R is gas constant. So similar, we are calling this equation number 1. Similarly, for second case, log K2 is equal to log A minus EA divided by 2.303 RT2. Calling this equation number 2. Now consider we are dividing equation 1 by 2. log K, we are subtracting equation 1 by 2. Subtraction we are doing. So log A minus log B is equal to log A by log B. So log K2 minus log K1. We are subtracting equation 1 from equation 2. So log A will get cancelled. So EA divided by 2.303 R into 1 by T1 minus 1 by T2. We can take LCM T1 T2. We can write it also T2 minus T1 divided by T1 T2. So this is the equation in which log K2 minus log K1 can also be written. So this is the integrated form of Arrhenius equation. This is the derivation of Arrhenius equation. From this we can calculate the rate constant at two different temperatures. Next we will move on to activation energy, that is energy of activation. So we have three parameters, that is threshold energy. This is the minimum energy that should possess by a reactant molecule to form products. Whereas internal energy is the energy already exists in the reactants are called internal energy. So whereas activation energy is the minimum amount of extra energy that should possess by the reactant molecules to undergo reaction to form products. That is, apart from internal energy, we have to supply some more energy to the reactant molecule to meet the threshold energy to form products. Hence internal energy can also be written as internal energy plus energy of activation will be equal to threshold energy. You can see in the energy profile diagram here, we are plotting a graph energy versus reaction path in which reactants have a higher energy than the products. This is the pattern in which reactant should have a higher energy than the product, because more the energy, lesser will be the stability. Product should have less energy to have more stability. So you can see this is the activated complex. Activated complex is achieved by supplying extra amount of energy of activation. This is EA, and this is the internal energy. Internal energy plus energy of activation will give us threshold energy. So next we will discuss the effect of catalyst. You can see in the energy profile diagram in which energy versus reaction path, the graph itself explaining that introducing a catalyst will decrease the energy of activation value, so that it will ease the product formation. It will make a different path for the product formation. So activated complex in the absence of catalyst will have a more energy of activation. It requires more energy when compared to activated complex in presence of catalyst. Next, we will discuss simple collision theory. As the word is suggesting, collision takes place during the reaction to form products. Reactant molecule will undergo collision that should be an uh, regular interval, and which will give us the product. The orientation, the collision should occur in a proper orientation so that we will form products. So example, formation of hydrogen iodide from hydrogen and iodine molecule. So here in the first reaction there is no proper orientation of collision, hence we will not get the products. Whereas in the second case we will have a proper orientation, H and I, we will form a products. We have a drawbacks of this simple collision theory, because we are not able to calculate the steric factor from the geometry. That is, simple collision theory is applicable for simple structured molecules, and it is also applied to gaseous reactions and gaseous reactant molecules, and it will not provide any information of effective collision. So before collision the complex should be activated. The activated molecule, when they come in contact, when they collide, they will form products. The normal molecules without excitation will not form products, and it does not account for the role that the internal energy might play in the reaction. So it is not discussing any internal energy parameters. Hence we will study activated complex theory. In the activated complex theory, for the explanation sake, we are considering A2 and B2 are the reactants. So you can see the reactants AA, BB will form an activated complex AABB ash. So after the formation of activated complex, it will form the products AB plus AB. So for this, the formation of activated complex is actually a reversible process. After activated complex, we have a K2 as rate constant. So for this, the concentration of transition state is very important, and the rate at which activated complex decomposes is very important. These are the two parameters which is very important to explain the activated complex theory or the transition state theory. Next, this is the parameter, this is the energy profile diagram of exothermic reaction and endothermic reaction. In exothermic reaction, reactants will have a higher energy than the products, whereas in endothermic reaction, reactant will have a lesser energy than the products. So products will have a higher energy. In order to proceed endothermic reaction, the energy should be, heat should be supplied to the system, reaction system. In exothermic, heat is liberated to the surrounding, whereas in endothermic, heat is absorbed from the surrounding to the system. System is where actually a reaction takes place. This is the derivation where we are considering A plus B. We are getting K equilibrium. This is the equilibrium reversible reaction. This is the activated complex. Molar concentration, AB ash is the activated complex. After some time, it will form products AB with a rate constant K2. So when we apply equilibrium constant equation, K of equilibrium ash will be equal to molar concentration of products divided by molar concentration of reactants. That is molar concentration of AB to the power ash divided by molar concentration of A into molar concentration of B. So we are taking AB, molar concentration of AB, and when rate at which activated complex decomposes, that is K2, we can write minus dA by dt is equal to minus dB by dt will be equal to K2 into molar concentration of A into molar concentration of B. So substituting, we will get the equation number 1, where gamma is called frequency of vibration at which activated complex decomposes. So this is the equation in which we can substitute this by Boltzmann equation, that is R divided by N is equal to K, where K is the Boltzmann constant, R is gas constant, and N is Avogadro number of molecules present in 1 mole of substance. So also we are applying a Planck's equation, that is E is equal to h mu. E is the energy, h is Planck's constant, and mu is the frequency. So mu is equal to E divided by h. E is kT, so we can write it as mu is equal to kT divided by h or RT divided by NH. So substituting the equation 2 in 1, we are getting the final equation as K2 is equal to K equilibrium ash into RT divided by NH, where R is the gas constant, T is temperature, N is Avogadro number, and H is Planck's constant. Next, we will move on to experimental methods for chemical kinetics. The number 1 is conductometric method, saponification of an ester. So saponification of ester is nothing but ester is treated with a base NaOH to give acid, sodium, salt acid and alcohol. So here conductance is nothing but the measurement of mobility of ions. More the mobility, more will be the conductance measurement. So as in general, OH minus ions and H plus ions will have a highest mobility in the solution. Hence, we will get highest conductance. See, we can consider C0 is the initial conductance measurement of the reaction, and CT is the after every time interval we are measuring the conductance, and C infinity is after completion of the reaction. So as and when the reaction proceeds, the OH minus ion concentration from NaOH will decrease. So hence the conductance measurement will also decrease. So when we consider this for initial concentration, A is proportional to C0 minus C infinity. x is proportional to C naught minus Ct, and A minus x is proportional to Ct minus C infinity. So we are substituting for the rate equation, that is A is equal to B. The initial concentration is the same. So K is equal to 1 by T into X divided by A into A minus X. So we are substituting and simplifying. Kt is equal to 1 divided by Ct minus C naught minus of 1 divided by C naught minus C infinity. So we are plotting a graph of 1 by Ct minus C infinity against time t. We will get a straight line. So when we calculate the slope of this straight line, we will get the rate constant K. The rate constant K unit will be per mole per minute. So this is the method, graphical method, and conductometric experimental method to determine the rate constant of second order reaction. Next is spectrophotometry. So spectrophotometer method. This is the colorimetric study of kinetics of oxidation of indigo caramine IC solution by chloramine T, that is CAT solution. So this is the reaction. IC is treated with CAT solution to form SAA and the other byproducts. So here we are checking the OD, that is optical density of the reaction, spectrophotometer, in which OD naught is the initial optical density before starting the reaction, and ODT is the after every regular time interval we are checking the optical density using the instrument, that is OD naught. So we have an equation K is equal to 2.303 by T. T is the temperature, T is the time, log of OD naught divided by ODT. So where OD naught and ODT are the optical densities of reaction mixtures at time T is equal to 0 and time T respectively. We are plotting a graph log OD naught divided by ODT against time T, which gives us a straight line. When we calculate the slope, when slope value is multiplied by 2.303, we will get the rate constant equation. The procedure is, first we have to take 98 cc of buffer solution and 1 cm cube of CAT solution in one reagent bottle, and in other reagent bottle we have to take 1 cm cube of indigo caramine solution, and we have to kept in a thermostat water bath to attain same temperature. After some time, after 5 minutes or 10 minutes, we have to add these two solutions. The total reaction mixture will be 100 cm cube. As and when we mix, suddenly we will take the optical density reading for that reaction mixture. That will be our OD naught. After every time interval, like 2 minutes interval, we will check the optical density. We will get ODT. And by using the above equation, we will calculate substituting K is equal to 2.303 by T log OD naught by ODT. So we will get the graph plotted, and we will check the K into slope is multiplied by 2.303 to get the rate constant equation.